A $40,000 drone destroyed a $500 million radar, and only 15 of these sensors exist in operational service. The system was engineered to intercept ballistic missiles at the edge of space, not to survive what flies below radar coverage. Most coverage focuses on interceptor speed and kill probability, but the real architectural failure was never the missile itself. This documentary explains how one radar became the single point of failure inside America's most expensive mobile missile shield. The story begins in 1991, when Iraqi Scud missiles exposed a critical structural gap in American ballistic missile defense. Patriot batteries attempted intercepts during Desert Storm, but post-war analysis revealed that most engagements failed to destroy incoming warheads. The Pentagon needed a system that could guarantee destruction through direct collision, eliminating the warhead without relying on proximity blast. Lockheed Martin began development in 1992, building an interceptor that would destroy targets through direct physical collision alone. The THAAD interceptor carries no explosive warhead, relying entirely on kinetic energy generated by direct impact at Mach 8. A single-stage solid rocket booster accelerates the kill vehicle from 0 to 9,000 kilometers per hour in just 6 seconds of powered flight. Each battery fields 6 truck-mounted launchers carrying 8 interceptors apiece, controlled by 2 operation centers and 90 soldiers. But the entire battery depends on one sensor, the AN TPY-2 radar built by Raytheon and spread across 5 40-foot trailers. This radar detects incoming ballistic missiles at ranges exceeding 1,000 kilometers, tracking warheads and discriminating decoys throughout flight. It performs search and fire control within one platform, meaning the same radar finds the threat and guides the interceptor all the way to impact. THAAD entered service in 2008, marketed as the most capable mobile ballistic missile defense system ever fielded by any military. Understanding what makes THAAD unique requires examining the kill vehicle, the component that physically destroys the incoming warhead through direct collision. The kill vehicle separates from the booster mid-flight, activating an infrared seeker that locks onto the thermal signature of the target. Divert thrusters adjust the trajectory in the final seconds, correcting the flight path with precision measured in centimeters at closing velocity. Engagement altitude ranges from 100 to 150 kilometers, meaning intercepts happen at the boundary between atmosphere and space. From initial radar detection to kinetic impact, the entire engagement cycle completes in under 3 minutes against most ballistic threat profiles. Each M1120 launcher truck carries 8 sealed canisters, and reloading a fully expended launcher requires approximately 30 minutes of sustained crew work. 6 launchers spread across a wide defensive perimeter, all linked by secure data connection back to one central fire control station. The TPY-2 performs wide-area search and precision tracking, discriminating warheads from decoys and guiding interceptors to targets. Its field of view covers 120 degrees, meaning a single battery monitors roughly 1/3 of the surrounding threat horizon. The radar platform spans 5 40-foot trailers, mobile enough to relocate but large enough to identify from commercial satellite imagery. Here is the engineering trade-off that defines this entire platform. One radar does everything, and destroying that radar blinds the entire battery. Without the TPY-2, a battery can still fire using external sensor data, but with severely degraded coverage and limited engagement effectiveness. The Russian S-400 deploys 5 to 6 radar types per battalion, maintaining full tracking capability even after losing individual sensor elements. Western doctrine chose one perfect radar over several adequate ones, mistaking concentration for engineering elegance rather than vulnerability. That approach worked in controlled environments, but nobody stress-tested what happens when the defender itself becomes the attacker's primary target. If you want to understand the systems defining modern missile defense architecture, subscribe to this channel for one system per documentary. But the architecture met real combat pressure, and the math collapsed, because the economics of this system favor the attacker entirely. One TPY-2 radar costs just shy of $500 million, according to the Missile Defense Agency fiscal year budget. A complete operational battery with 6 launchers and 48 interceptors costs between $1 and $1.8 billion before deployment. Every single interceptor launched from those tubes costs $12.7 million, and the battery carries only 48 rounds total. Saudi Arabia signed a $15 billion contract for 7 THAAD batteries, with 360 interceptors and 7 TPY-2 radars. Only 15 TPY-2 radars exist worldwide across all American deployments and allied nations, and Raytheon cannot produce replacements quickly. Each destroyed radar creates a gap that takes years to fill, because the production line builds sensors in small batches with long lead times. During 12 days of Iranian barrages in June 2025, THAAD fired 150 interceptors over Israel. That single engagement consumed 25% of every THAAD interceptor the United States had purchased across all prior defense budgets combined. Within 7 days of the 2026 conflict, Iranian strikes degraded roughly $2.7 billion of American radar infrastructure. The drone that destroyed the AN TPY-2 in Jordan cost approximately $40,000, striking a sensor valued at $500 million. That produces a cost ratio exceeding 12,000 to 1, favoring the attacker in every single engagement, regardless of interceptor performance. The defender must intercept every incoming threat to survive, while the attacker needs only one successful strike to disable the entire battery. The economics broke before the hardware did, because production cannot match consumption when each defensive round costs 300 times more. THAAD achieved its first confirmed combat intercept in early 2022, when a UAE battery destroyed a Houthi ballistic missile over Abu Dhabi. That single engagement validated the hit-to-kill concept and generated immediate international demand from nations facing ballistic missile threats across the region. In June 2025, Iran launched massive ballistic barrages toward Israel, and THAAD batteries fired continuously for 12 days. Performance remained high, but consumption was catastrophic, burning a quarter of the global stockpile in under 2 weeks. On February 28, 2026, Operation Epic Fury began, and Iran retaliated with simultaneous strikes across the Gulf region. Iran targeted the sensors instead of the interceptors, aiming to blind the entire detection network before saturating what remained on the ground. Muwaffaq Salti Airbase in Jordan hosted a full THAAD battery deployed in mid-February, with 6 launchers and 1 TPY-2 radar. The base held over 50 American fighter jets, including F-35 and F-15E aircraft, the largest tactical concentration in the theater. On March 1st or 2nd, Iranian drones crossed 800 kilometers of defended airspace and struck the radar compound directly. Satellite imagery revealed 2 4-meter craters beside the radar, with all 5 trailer platforms either destroyed or severely burned. CNN confirmed the destruction and Pentagon officials acknowledged the loss, while declining further comment under operational security restrictions. The battery's launchers and 48 interceptors survived physically, but without the radar, they could not detect or engage incoming threats. Parallel Iranian strikes hit THAAD radar shelters at Al Ruwais and Al Sadr in the UAE, damaging buildings that housed transport vehicles. Prince Sultan Air Base in Saudi Arabia showed smoke rising from a charred radar shelter on March 1st, with debris scattered across the compound. Iran had not defeated the shield by overpowering it with volume, but by surgically removing its eyes across an entire operational theater. The American response was immediate. THAAD batteries began relocating from South Korea to the Middle East, straining Pacific defense posture in the process. South Korea's president publicly warned against over-reliance on American security commitments as critical missile defense assets departed the Korean peninsula. The Army announced plans to transfer THAAD from Missile Defense Agency control to Army management by fiscal 2027, streamlining operations. A proposed THAAD variant would triple operational altitude with modified boosters, extending intercept range beyond 290 kilometers. But no proposed upgrade fixes the core flaw exposed in Jordan. 1 radar per battery remains the baseline across all variants. The lesson from Muwaffaq Salti is architectural, because a system built around 1 irreplaceable sensor creates exactly 1 irreplaceable target. Distributed sensor networks, where multiple cheaper radars replace 1 expensive platform, are the emerging alternative to single-point dependency. Integrating airborne sensors from F-35 fighters and ship-based Aegis radar systems could remove the single ground-based radar as detection source. The Army Integrated Battle Command System aims to connect every sensor node into 1 unified network for coordinating interceptor fire. But integration across services and allied nations requires software discipline that no hardware upgrade or contract can deliver alone. THAAD remains the only mobile platform capable of exo-atmospheric ballistic intercept using kinetic kill technology beyond 200 kilometers. Its interceptor engineering is extraordinary, but its architecture carried a vulnerability that decades of testing never managed to reveal. It took a $40,000 drone to prove that the most expensive mobile radar on Earth had no dedicated defense of its own. THAAD carried the upper tier on a single expensive sensor, and Iron Dome carries the lower tier on completely opposite economic logic. The next documentary covers the system that intercepts for $60,000 per round instead of $12 million, Iron Dome.